to deal with the Riemannian case. Now, during the first two lectures, we managed to do the following. From boundary spectral data, that were the eigenvalues and the traces on the boundary of the eigenfunctions of the Riemannian equation, we built up the boundary distance representation R of n of this unknown manifold n. And this is just nothing more as all possible distance functions from the points inside to the boundary point z. So for any x gives you one, this function is not Rf of z. So this is a set in CDN, and it is yes, and we can treat it as a metric space with the metric that is just inherited in C. So denoted L infinity metric. So we have this metric space Rn with metric d infinity. By the way, you can completely utterly forget and how did we come from BSD boundary spectral data to R of n. From now on, we'll be just working with Rn. And the division of Rn is following. It's just all distance functions from to the boundary when you fix point inside and the right point in the boundary. That gives you one function, then you go to different axes, that gives you a set of functions. So what we did last time, we managed also to show that if you look for this metric space Rn with a metric d infinity, so this is just d infinity between two r's, R1, R2 is just the usual L infinity norm. Yeah. So that this metric space that is in our disposal, Rn with d infinity, is actually homeomorphic to n with the metric that is generated by Riemannian metric d. So therefore, we recover the topology of unknown n. Now, as I said, our next goal will be to find the homomorphic differential structures. Of n. Well, what we have now at disposal is this R of n. So what we are going to do is to build up a differential structure of an R of n, namely, what does mean differential structure? To introduce coordinates. To introduce coordinate system around different points, and points here, remember, these are functions. So that R will become a diffeomorphism between R of n and n. So our goal is to build coordinates near any point R in R of n. So these coordinates suit well for the manifold. See? What we have only this distance function. So therefore, our coordinates will be based on distances. That's what we have. So how we do it? Okay. Let me recall what we did. So that is our Dn. And then for any point x0, there was a nearest point of the boundary, z0. There are several of them, but at least one nearest point of the boundary. And this is the shortest is actually normal geodesic to the boundary. Then you can show, well, that is some small result, that you can if you look for the polar coordinates at point x0, so you send geodesics under the angles that are close to this angle. So this is the direction, normal direction, when you go from f0 normally to the boundary. So this is normal. Now if you, let's go to psi 0. If you shoot geodesics from x0 under the angles that are close to the psi 0, then the geodesics will be normal to the, not normal, transversal to the boundary. And they produce a good coordinate system here. So, okay, so once again, if you shoot the geodesics that have direction close to the direction of geodesic that comes normally to the closest point of the boundary, that will be still the shortest geodesic to the boundary. You can look now backwards. That's the problem, that's the inverse problem. So you first look at direct, then you turn your head and look from the other side, and that's become the inverse problem. coming to the point Z, and now you can see you can go back along the geodesic, right? So you shoot geodesic backwards and come to x0 from Z, and Z is close to Z0. So once again, if you change your xi, say it's unit xi, in the repeat of xi0, you get the whole vicinity of the point Z0. Imagine you have a cone, and then intersect the cone with something that here is perpendicular. So you have something open n-1 dimensional set on the boundary. Okay, so that means that because it's a whole cone of direction. So when you're going backwards, so this is psi of z, and this is minus psi of z, right? So if you go from z shortest way to x0, that will be direction of these geodesics minus psi of z, and they form the whole cone. Since they form a whole n-1 dimensional cone, you can choose n linear independent vectors. So we can choose z1, zn near z0, so that if gamma I of t is the shortest geodesic from zi to x0, then reaching x0 at time ti. The word time means actually the length, the arc length. At time ti, then gamma dot I at the time ti are linear independent.
You can do this constructively.
They will be constructively. Let me explain how. Then I show how to choose them. It's not constructive, but there's a test to check that this is proper thing. Okay. So what does it give us? Well, let us see. Let us introduce the distance from this point z I to variable. So now we take the points near x, some vicinity u. Let u be some small neighborhood of x0. Then for any x, for x belonging to this u, there is a geodesic. Let me draw a larger picture. I put it Z1. So this is Z1, and this is the corresponding vector. And if you take some other point in the vicinity, say this is x, then there is a unique shortest geodesic that goes to x. And there's the vector. And everything is continuous. Therefore, if you're not far from x0, this u is small, then if you denote, then there is a unique shortest gamma I of t and x from zi to x. So gamma I of tix is x, and well, it's just continuity. Gamma dot I of ti and x are linear independent. Okay, so let me draw other vector. This is Z2, and this is this vector, and this is this vector. Okay. Now, all this can be proven, but you can do all these things. Just imagine this as just straight lines, and when you change direction, the vectors were linear independent. You change a little bit the direction, they're still linear independent. So what does it give us? Okay, what is gamma dot I geometrically? Well, we introduce it, look for the function for the point z, the variable point x. Now here we fix x, z, and change x. In Rx, we fix x and change z. Now this is fixed. What will be the level surfaces? D equals to constant. This will be spheres. So let me draw a little bit distorted spheres, but they are still spheres, means they have no singularity, so something like that. Yeah? And that's probably sphere through like that from through x0. So we have that constants are spheres centered at z, and if gamma from the point z, if you look for gamma from the point z to t, and this is x, then gradient with respect to x of dxz will be gamma dot z of t. There's nothing surprising that we know all the time that radii are perpendicular to spheres, right? So this is the same story. So if you look for these points Z2, this is the surface distance from Z2 is constant, and this is geodesics that comes to this point, and the geodesics is perpendicular to the surface. So the Z dot is great. Okay. Therefore, let us put it back. Now we take not all z's, but take the z1, z10. Then, therefore, if you look for this matrix, dxi of di of x over ddx d over dxj. So now di is actually d from x to zi from our chosen points. And then determinant of this matrix is non-degenerate in x0 and its vicinity and its neighborhood. Yeah? Because this is just the matrix made of these gradients. And we know that these gradients, these gamma dots, they're linear independent. So therefore this matrix is non-degenerate. And by inverse function theorem, there is a vicinity. Thus, in some neighborhood of x0, x will be x of d1 dn. So, yes?
How are you taking the spheres? That length, first length.
Yes?
Yeah.
Well, you fix the center of the, and you look for the all points at the same distance.
From boundary. Yeah.
Sure. From any point, you have a metric space, you fix the center, look for the points of the fixed distance. What is this? The sphere. Okay? And the geodesic will be perpendicular to the sphere. It's a radius and a sphere. Radius is perpendicular to the sphere. Okay? So that's written here. Okay? Now, therefore, what stands here will be actually the gradient. But strictly speaking, it's not a gradient. It's a differential. But then you need to relate it. Maybe as to, do you know the difference between differential and gradient? Let me tell you. So, you have a function. Say any function, f of x. Then you can find differential. That will be just d1 of f, dn of x, right? So this is differential. In the Riemannian geometry, this is not a vector, it's a whole covector. To make a gradient, so gradient f will be gij of x, gif of x. So it has components now at top. But since these guys are linear dependent, this guy is also linear dependent. So therefore, you have a matrix where the columns are linear dependent. So it's not degenerate. And by this function theorem, we can now represent x in terms of d's. What does it mean? That these d's are good coordinates. Okay? Therefore, thus, i.e. d, that is d1, dn, are good coordinates. These coordinates, by the way, but first of all, they're used in real life. You know, there's in geodesics, they put these, I don't know, sort of things, and then they measure distance from them, and they have several of them, and then they find the point because it lies on this distance, say 1 kilometer from this pillar and 2 kilometers from the other pillars. So that's what they actually use to make the map. So this is exactly these coordinates, and they're called in our case distance coordinates from the boundaries, because I recall you what is this d. Di is of x, is distance from x to a fixed point that are on the boundary. So the distance coordinates from the boundary. It's hot. What we have in our disposal is we work only with these distances, and we have Rn. So we have in our disposal all possible distances. Okay? So now we return back to Rn and try to check how we choose these distances, these distance coordinates. Still, when we are told, you remember that actually n is behind the wall. It's our mental construction. We can't do it. We can do only in reality things with Rn, with the functions. So how to transplant these distance coordinates from Pn, from n to Rn. Yes.
Did we choose the ZIs in some particular?
Did we choose what?
Did we choose the ZIs? The Zs in a particular Z.
ZIs.
Z, yeah.
Of course. Look, once again, the first term is, we say that these ZI do exist. I didn't yet say how we can find them. I'll go to do that. Because, why they exist? Because there is a whole cone of good directions. Because the whole cone, there are n linear independent. Right? So we know that they exist. Now, how to find them, we'll discuss now. Okay. That's how we're going to translate. Okay? First of all, basically, it's not constructive procedures. It's more or less say, well, you give me ZIs, and I can check whether they're proper ones or not. Okay? First of all, we look for f. Take R0. Takes any function from this R of z, Rn. it corresponds to some x0, so assume that it corresponds to x0. If you don't know x0, you just pick up any r0 from R of n, and it corresponds to some unique point x0. Take R of 0, then when epsilon is small, b epsilon r in R of n is satisfies. So this is a ball of radius epsilon because metric space centered with R0. Satisfies that if you put R minus 1, so we go back to x0 of this b epsilon, that belongs to this neighborhood U. Yeah? Because it's the homomorphic and topology is the same, you can make the epsilon so small that the image will lie in this, it will be something like that, right? So that is where you have good x coordinates, good d coordinates, i.e. d coordinates corresponding to some unknown z1, zn are good. How? We don't know that one. We want to choose R1 of z, Rn of z in this U epsilon, so that if we take for any so that they parameterize this U epsilon d epsilon of R0. Imagine like that. You know, you have a bunch of functions that lie in the epsilon vicinity of R0, and then you say, okay, well, if I take the points function R1, Rn, then they give me some value at the points at some points z1, zn, so that these points, these values of this function are one-to-one correspondence to how to say this? Let me see if I wrote it. No. Well, different. Once again, so we have this small ball of radius epsilon in the space R of n centered at R0. Now we choose points z1, zn near z0. And remember that 0 is the nearest point to R0 on the boundary. So that R of Z1, R of Zn parameterize this ball of radius epsilon. Meaning, that, roughly speaking, the following. You look at points and look for the values of the functions R from this B epsilon ball. And if you measure the values of the function upon z1, zn, for different r's, these values look different. Okay? So therefore, to each this value, there corresponds only one function, and vice versa. This gives us coordinates d, that will be exactly this r of z1, r of zn, and d forms an open set near d0, that is r0 of z1, r0 of zn. This is the central point. Okay. Well, that gives us some coordinates, but these coordinates are not necessarily C-infinity smooth. They are topological coordinates, but there may be some singularities. How to check that they're C-infinity smooth? Well, that means the following. They are these coordinates d equals to d1, and we call it d1, and we call it dn. d1, dn are smooth coordinates if you have the following. For z close to z0, RZD are smooth with respect to D. So what is written here? You see, we have a family of function Rz that obtained in the absolute Boltzmann with R0. This family can be parameterized by parameter D. So I have a family of function R of Z and D. Okay? And they correspond, when we write D, we run over this ball of radius epsilon centered in the point R0. So when Z is close to Z0, we should require that this function is smooth with respect to D. Then this is a smooth coordinate system. Okay? Basically, it's not really constructive. It's a check. You give me Z1, Z10, and I check whether it works or not. Okay? I know that there is a choice because we prove that when we were behind the wall, we know that there are these Z1, Z10 that provides you proper distance coordinates. So now we try to check that I took this on this point. Are they good? Well, first of all, there is such a small vicinity of R0 when they're parameterized. They're 1 to 1. And then if Z is close to Z0, you have also smoothness of this function. So this provides differential structure on R of n, which is diffeomorphic to differential structure on n. It is diffeomorphic just because how we did it. We first looked behind the wall and said, all right, there are these distance coordinates. Then we find them, and then we can show that if we choose some coordinates that satisfy all these conditions, there will be coordinate transformation from the good coordinates that somebody behind the wall find for us. Okay? So therefore, it requires some work. But anyway, so therefore, these coordinates are compatible with original coordinates on n, and this gives a diffeomorphic structure over n that makes it a diffeomorphism to and R is diffeomorphic. Okay, so we do with satisfy. It now requires to find the metric tensor. Now we want to Riemannian structure on R of n. Now we treat it as a differential manifold, which is isometric to G. So what we are going to do, we're going to build some metric G capital. So we build metric G capital in here, and so that R makes a isometry between Rn with metric G capital and n with metric G. And this is the important picture. This is the important picture. Let's return to the same picture. Let me take it again. So this is our point. No, I have colors. So I have the whole vicinity of the point Z0 from where geodesics come to X0. So this is Z0 with X0, and then the whole vicinity of I have the whole cone of directions that geodesic from Z in the vicinity of Z0 goes to the point X0 and provide this cone of directions, right? And I have these functions. These functions are D of between Z and D capital. Now D capital is D1. D of D. It's horrible. There we call it tau. So tau of, no, R. You remember, so all the distance functions in the absolute vicinity of R0 can be parameterized by D. We already did it. What do we know? We know the following story, that that is somewhere here or here. That's what we know. Now, recall that sort of if you take the D with respect to, D tau, the differential of this function dr with respect to D, that will be the covectors that correspond to these directions, right? This is G. Say okay, maybe I write it this way. Di of R of x d. So this is differential with respect to di. At the point d equals to d0, what is that? This is G ij of what? Of the gradient of the gamma dot j from the point, here is z, from the point z to the point t. So this is this vector, and to go from the vector to the covector, we allow the index. But what is the gradient? So what is the velocity? So the gamma dot is the velocity of the geodesic. What's the velocity of geodesic? In the corresponding metric. It's 1. So you know that these guys satisfy the following conditions. That gamma ij, the gij gamma dot z I, gamma dot z j of t is 1. That's the length of this vector. If you write it, if you say, okay, in the form of the covector, you get the following. This is according to the following condition. That gij at D of di rzd at d equal to d0, dj r of z d at the point d0 is 1. Okay, just plug, express this. I mean, you can go from gamma to r, and that is exactly equivalent to that. Okay, and we have a whole. So we have what we have now. We have this function r of zd. Therefore, we have its differentials. So, but we have constructed r of zd for d near d0 and z near z0. Okay. By the way, this object is called, dr, right? Dr is just d1 of r zd, dn r of zd. So this is the differential. It's all derivatives, nothing more. And we know, what do we know? We know that dr of zd for d equal to d0 form an open code. Well, it's not open code. It's actually came an open set on the unit sphere of four directions. Of four directions. Four directions. Let's go back to this picture. Look at those two vectors. They give you, in two-dimensional case, they give you something like that. So they all have length y1, and they form an open set on the unit sphere of directions. When translating it in the language of coded differentials, that means that these codifferentials, when z runs, when z runs over some vicinity, over some neighborhood, of z0. So if you just go from the vectors to covectors, it exactly tells you that these differentials, when you take differential at the point equal to d0 and vary that near z0, give you an open set on the sphere, but sphere not in the tangent space, but in the tangent space. Okay? So we have a set of an n-1 dimensional set of covectors, and we know that have length 1. We don't know the metric, but we know that have length 1. Thus, I put G capital because of D. Gij at the point d0 of di r z d0 dj r z d0 is 1 when z is near z0. But that's it. You have a whole bunch of covectors, and they have all length 1. They all satisfy this thing. There's a quadratic thing with respect to z, and this uniquely determines zij. Of d0 and d nearby. answer that's actually, it's an analytic function that you know on the open set, but just look at the following simple case.
So before you lay that, I have one question.
About that?
Yes. So you said the smooth structure is determined by the RZB if they are smooth.
Yes.
So suppose I give you a function f on Rn or that neighborhood. I want to test whether it's smooth or not. How will I use the RZB function to test my smoothness of my function?
I have the function f on there.
So you have a function f on that manifold or the neighborhood, right?
With Rn.
Right.
Yes.
So the differential structure you define by saying RZB is smooth. Is that enough to define all? Or
yes.
That's what I was wondering how.
Yes. So you have not arbitrary function. You have only the function with Rn. Right.
Right. So suppose I have a smooth function.
You know, just have a function R of Z, and this R in the epsilon vicinity of R0.
Correct.
Okay. You first find whether Z1, Z10 satisfy the following condition. You take any function, you have two different functions from this epsilon vicinity. You look for the values of the points Z1, Zn, and the value should be different. So that means that you can parameterize all functions in this vicinity by d1, d2, dn. Okay?
Right.
So basically the distance to some particular points. Right? Then you take, this is topological coordinates. It gives you,
right. Yeah.
now you want to check that it's smooth.
Correct.
So smooth means that maybe in some smaller vicinity of Z0, you take a function, maybe it's not epsilon, but epsilon over 25. You take a function, R of Z, and Z runs at this small thing, and then you look for the following. So you have this function R of ZD,
And so for different z's, it's a smooth function, correct? That's the only condition.
No, Z is fixed. Z is fixed, and that should be arbitrary but close to Z0.
Correct.
So then you fix this Z close to Z0, it becomes function of D, and this should be smooth. Okay?
Right, that's a condition.
That's a condition.
Right.
Okay?
So
if this is satisfied when Z is sufficiently close to Z0, then our D1, Dn are smooth coordinates. Okay? And that is the saw behind the wall. Okay? So that is done. So now we have done everything. Just let me tell you how this is well, I'm not going to prove it somehow that if you have this expression equals to 1 on some n- dimensional set that correspond, then you find this Gij unique. Let's say two-dimensional thing. So let's say that this is your one-dimensional set that you know that. So this is psi1 and this is psi2. And you know that this is your d towers that live here. And you know that for any covector, but forget about coordinates, for any vector here, you have that Gij of psi I psi j should be equal to 1. Well, take for example just the vector psi that is 0 psi 2. This vector. What gives us? It immediately gives you g to 2, right? And then take this one and say some other 3 linear independent. And you can see that it's, in the two-dimensional case there are 3 variables, g11, g22, and g12. So you already find g22, then you try this vector, and they give you g12 and g11. So the idea is to have so many vectors or covectors that satisfy this condition that it uniquely defines Gij. You will ask me, how is sure that there is Gij? I don't know, but we know that there is one, and that's how to find it. Okay.
Slava?
Yes?
So once you find this R of n, the wave equation is not relevant anymore?
The question is?
Once you find this R of n,
yes,
then everything can be determined just based on this information?
Yes, that's what I said.
The wave equation is not...
This part was done during the first 2 lectures. We can forget about say, okay, we have R of n, let us show that we can find the Riemann manifold Ng up to the topology, up to the isomorphism. Yes. So this is we had 3 steps the first step was this logarithmic identity and octave result that give you a possibility to find these geometric L2 small subspaces, L2 gamma T. That's the first step. And it's an analytic step. Then the second step is sort of geometric, but sort of when we intersect them and they correspond to the slicing procedure. So that is, well, geometrists wouldn't call it geometry, but for us analysts look like geometry, right? From here you find R of n, and now this is the third step: how to equate this R of n with the structure of a Riemannian manifold, which makes it isometric transition. And the three steps: topology, differential structure, metric structure. That's it. Here is part. And now I go to the second part, Lorentzian manifolds. And eventually what I'll do is similar story. I will embed an unknown piece of Lorentzian manifold in the space of functions. In this case it was space of function on the boundary, but maybe some other space of function. And then I will look at the space of function and say, oh, this space of function tells me topology. So I can embed this space of function, this topology that is make it homomorphic to the piece of manifold. I can create by unique way the differential structure on this space of function that makes it diffeomorphic to this part of the manifold, and then to almost find, you'll see, it's almost find the Lorentzian metric on this space of function that makes it conformally isometric to the part of Lorentzian manifold. Okay. So that is right. But I don't know how you, I think that when I come to this business, my knowledge of Lorentzian manifold is just Minkowski space R1 cross R3. So therefore, probably I spent some time for the crash course, 1 hour, less than 1 hour, on some properties, geometric properties of Lorentzian manifolds. Do you mind?
Yes.
And that is our goal, except that it is not R of n, but something different. But topology, differential structure, remain Lorentzian structure. Okay. So once again, you recall that you know by M, it's Lorentzian manifold of dimension n plus 1. Because there will be like n space dimensions plus time dimensions. Well, this is Lorentzian manifold is differentiable manifold with Lorentzian metric tensor. G is Lorentzian metric. If in local coordinates, but actually it will be then any coordinates, it is a symmetric matrix, smooth of course, everything is smooth. I'm a very soft person. Of index plus, minus. So it's n pluses and 1 minus. N pluses correspond to the space directions and minus corresponds to the time direction. So what does mean this? You have symmetric matrix. You can make it diagonal. So if you look at that, it will be n positive eigenvalues and 1 negative eigenvalues. Example, Minkowski space, M4. And that is special relativity. So the metric will be dl squared will be minus dt squared, or in our case it's dx, right? dxn squared plus dx1 squared plus dx3 squared. Example 1. Example 2. Bit more interesting. So this is, it will be 2-dimensional, so this n is 1. maybe it's better, but anyway, this dx1 to the power 2, dxn to the power 2. So this is the case of S1, one-dimensional, is actually a circle, multiplied by R1. So you go around the circle, that's x1 that changes. You go around time, that's x2 changes. So the L squared will be the same.
I'll ask you one question. So you said you're going to represent this Riemannian manifold in some way. Are we doing an inverse problem, or are you just trying to?
We are doing inverse problem. We are doing inverse problem of astrophysics or astronomy.
So you haven't described.
Okay. Yeah, no. To describe, I need to introduce the object. I pronounce you.
Sure.
So 25 words out of which you don't know 24. Okay. Okay, so that's the thing. That's the Lorentzian manifold. Now, if you look at so of course it's a very, very simple one. In general, what you have the matrix Gij, so your dl squared is Gij as usual. The same like in the Riemannian case, the only point of this matrix, so it is n plus 1 by n plus 1 metric, and it has one negative eigenvalue and n positive eigenvalues, right? So therefore, if you look at all directions, so you look for the direction, you take a point x, so take x and look for all directions. That is what is called the tangent plane over x. But it's actually, well, after all, they're not living in R3. They're living in some part. We're living on this. If you're living on the surface of the Earth, it's not R2, it's curved, right? But I can say, well, go there, 10 kilometers. You understand what I mean, right? So it's a point and direction, but direction is also the vector. So it's where to go and how far. That is vector, right? So we take all directions psi, and then we can classify them into 3 different types. So into time-like, light-like, and space-like. So psi is time-like. If G, I, J, so remember that this is a vector from the point x, so that's why I put here x. Gij at the point x, psi I x, psi j x is negative. It is light-like if Gij x, psi I x, psi j x is 0, and that gives a direction of propagation of light. That's why it's called all gravitational waves, if you prefer. I prefer gravitational waves because if you find gravitational waves, you definitely get a Nobel Prize. And of course, there is a third possibility, space-like. If Gij x, psi x I, psi x j is more than 0. Okay, so these first two are called also causal. Because physicists say that, well, if you have, by the way, a point in Lorentzian manifold is called an event in physics. And you can say that event, anyway, causal means that the point P, the event P, can affect event Q if there is a causal line from P to Q, right? You can't affect something at the same time that is far from you. Everything has a finite speed of propagation, the speed of light. You can't go further. Okay, so let us look for this example. Which vectors here are light-like, which vectors are space-like, and which vectors are time-like. So actually, these two examples are similar because at any point, this is just the tangent plane is just R1 by R1. So let's look at this one. What about these vectors? 1, 1, 0, 2. Is it time-like, space-like, or? It is light-like, because if you look this, so this will be once. So here Gij will be the following. It's delta Ij for Ij less than 3, and G for 4 is minus 1. Right? So it will be 1 squared plus 1 squared minus 4. So it is light-like. It's time-like. It's time-like. 1 plus 1 minus 4. And what about this vector? One half, 0, 0 to 0, 2, minus 1. It's like that. It's 1 half plus 1/4 plus 3/4 minus 1. So that's like that. So you see how to check it. If you look for the light-like vectors that satisfy this condition, they form two cones. So if they form, that's called a light cone. It consists of two parts. Well, and you would say that this is the future part and this is the past part. So light-like vectors psi form a cone of two. If you just cut off the center, they become disjoint of two disjoint parts. Future and past. At the moment, is somehow what you expect from physics, correct? Now there comes a question: can we equip the whole Lorentz manifold so that therefore all the time-like vectors? So inside it's time-like, right? It's time-like. They're inside the cone, and this is light-like, and outside is space-like. So can you say, okay, if I'm speaking this cone, say, well, this is the future cone, so this is a future-looking direction. Now you go to the next point nearby, and your cone will change, right? Can you prescribe to the whole manifold, to every point, the future direction that they change continuously from point to point? How do you think? So if you can prescribe to any point the future cone of directions, when we go to the next point, it's a little bit change, but so you can see it because it continues. So you can say, well, this is the same cone. It doesn't just suddenly jump down, and then you go all the way through, return, and you have on the same future directions. The direction of the cone, when you go far around, doesn't change down. In this case, the Lorentz manifold is called time-orientable. When for any point you can change the time direction so that it is continuous through the whole Lorentz manifold.
So you're saying that you assume that can be done, or you could prove it?
No, it's not always the case.
It's not always.
No, and I'll give you an example. I mean, this is chatting, so therefore don't be very much distracted if you don't understand everything. This is sort of chatting. So. Lorentz manifold M is time orientable or time oriented if there is a continuous and a smooth time-like non-zero time-like vector field. That means that at any point I prescribe direction of the time that is positive, and this prescription of direction is continuous, and that I do through a whole manifold. Okay. Now, it depends upon what is G. Say, for example, we look for the this two-dimensional case, and slightly more funny. Let me draw. Take the picture. It's not a picture. And so what I do then?
So
yes.
The non-zero time-like vector field, does it mean it's not zero anywhere, or
it's not zero. It is zero nowhere. Otherwise, of course, you can prescribe it here and there and zero in between. No, it's not zero everywhere. So that is my two-dimensional manifold, and I twist it and connect here, right? And then you see, okay, I do twist and connect here. So therefore, if I go that way, then when I go back, I go opposite way around. So if this will be the time direction, it will not time orientable, because I go that direction, but when I return, I go opposite direction. So this vector field dramatically changed, has a jump. But if I say, no, this is my time direction, and this is space direction, then I go back, I return to the same vector. You see, so first of all, this not time-orientable Lorentz manifold do exist, and it depends not only upon M, but also upon G. Okay.
But you could ask the question, right? So you twisted the manifold. So I'm just curious, so on any manifold, can you put a Lorentzian metric?
No. There are some topological abstractions.
So I was wondering, when you twist it, really cannot put a Lorentzian.
That's what I did.
Sorry?
That's exactly what I did.
So you put a Lorentzian manifold metric on it?
Yes, so that's what I did. So I made a torus, but it is torus with a twist. And this direction will be time direction, and this direction will be F direction. So it will be not time orientable, because when you...
I see,
it's just traditional thing of non-orientable manifold, like Möbius strip. Remember, in Möbius strip there are two directions. This strip, in this direction is fine, it's this direction that is bad. So I do the same trick. And yes, well, I mean, it's not the question of people from the last problem, but it's true. For example, at any manifold you can put a smooth Riemannian structure, but not in any manifold you can put smooth Lorentz. Okay? It's a it's a big science that I'm not doing long. Okay? So in physics, and since we are in applied mathematics, let's call physics, we assume that our Lorentzian manifold is time-oriented. Okay? So we work with time-oriented Lorentzian manifold. And now we have a break.